Good morning, good afternoon, good evening, wherever you are located. And thank you for joining me for this Understanding DC Systems Design webinar for AMETEK Solid-State Controls. If you don't mind, while we wait for everybody else to join, if you could comment in the comment section whether you can hear me or not, that would be absolutely perfect. So there's a little bit of a delay between when I speak and when I see your comments. So I'll just wait for everybody to let me know you can hear me. Good stuff. Thank you very much. So this is a webinar that we did in April of last year, and we are revisiting it because we had a lot of questions regarding the webinar, and there was some really good feedback for it. So we thought we would revisit it so people who didn't have the opportunity to see it last time can have an opportunity to see it now. And without further ado, it looks like we have quite a few people here, so we will move on with the webinar. So as I said, this is Understanding DC Designs. My name is Craig Williams. I'm the Senior Technical Manager for AMETEK Solid-State Controls out of the Stafford, Texas, just south of Houston office. We have a training center down here, and that is where I work out of. I have 20 years in the industrial UPS industry. For my sins, 20 years. I used to work in the North Sea oil and gas fields, going around installing, commissioning, and troubleshooting UPSs out there. Love my time there. And about 8-9 years ago, I moved to the US to continue what I was doing for the US market. I've worked with all major UPS and charger manufacturers. And before we go any further, I can assure you this is not going to be a sales webinar. I'm not trying to sell you on anything. This is just a purely technical webinar, okay? There will be a lag of around 15 to 30 seconds between when you hear my voice and when either I see a question or a comment in the chat bar. The platform that we use is called Webinar Jam, and it's got to convert this into iOS devices, Android devices, and obviously Microsoft stuff as well. And that takes a little bit of time to process. So from the time you hear my voice to me seeing you reply with a question, it usually takes about 15 to 30 seconds. So please bear with me on that. Webinar Jam does have a panic button. So if I lose connection with everybody, what I can do is I can press this panic button and it will create a whole new room for everybody. You will all be invited back into that room and we will carry on from where we left off. And a question that we get asked all of the time is, will the webinar be recorded? And the answer is yes. And we do two things for you. First of all, Webinar Jam, because you signed up for the webinar, you will receive a link for the recorded version of this. Now, the webinar version, you cannot fast forward, rewind, pause, or anything like that. It's treated as just a normal webinar. And because of that reason, what our fantastic marketing department do is they will convert that webinar into an MP4 and then upload it to our YouTube channel. And I think it usually takes 24 to 48 hours for them to do that. And that way you can play, pause, rewind, and go back to it whenever you want. We will not be sending the PowerPoint presentation. Thank you for the question already. Our PowerPoint presentations are proprietary, and we feel that you get more out of the video, and obviously you can replay it whenever you want, so you get to see the PowerPoint presentation whenever you want. And the webinar should last around about 1 hour, so that's what I aim for, and it depends on how many questions that we have at the end. And I've just started to notice that there is some background noise here. There's nothing I can do about that. And believe it or not, I'm not at home. It's not my kids. We actually have a dance studio next to our training center here in Houston. And the walls are obviously quite thin. So please bear with us with that. Okay. So our learning outcomes today are, we're going to try to help you understand the most common DC systems, understand what a DC system is designed for, discuss the advantages and the disadvantages of different designs, discuss power flow and general operation of each design, and then the fun part is discuss common misconceptions of DC systems that are out there. Okay. So here's the very basic one-line diagram overview of a rectifier charger DC system. Now, those three terms are pretty much interchangeable because there's a lot of misinformation about rectifiers, chargers, and DC systems. And in truth, they all use roughly the same technology to convert AC to DC. Now, I suppose a rectifier could be classed as a system that doesn't have a battery, but we tend to call them battery chargers because the rectifier does charge a battery. But the terms are interchangeable. You will hear me saying it multiple times during this presentation today. If I say rectifier, replace it with battery charger or DC system. It's completely up to yourself, but they are the same things. Okay. So you can see on the left-hand side, we have the AC input. That's usually for industrial systems, three-phase 480 volts AC. Then we have our our AC input breaker that goes into a transformer. And then we have our conversion stage here. We convert the AC into DC. Now, AMETEK Solidstate Controls uses SCR bridges, silicon controlled rectifiers. So that's our design. We then have a battery disconnect, and then that then goes to our battery, and then eventually you have your load circuits here. Okay, so that's just a very, very general overview of a DC system. Now, this is what most people would see is the standard single charger DC system that is out there. Okay, so you will have 480 volts being fed from your MCC, whether it's your emergency board or whether it's a normal board, from a bucket there, and then that will go to our charger terminals. And then inside the charger, you will have an AC input breaker. And as I said before, you will have this transformer, and then the rectifier will convert the AC into DC. And then on the charger itself, we will usually have a DC output breaker. And then the cables from the charger go to a DC panel. Now, there are many systems out there that aren't designed as maybe well as they should be, but you should always have a means of disconnecting the charger into the DC panel. So you should have a breaker specifically for your charger. Now, that could be the main breaker for the DC panel or a separate breaker for the DC panel, depending on the rating that's required. And then you will also have either a disconnect or a breaker for the battery as well, and you'll have your battery out here. Okay, so this is a relatively good system because if you needed to work on the charger itself, you could open this disconnect here. Your batteries would still be able to supply power to your load circuits here, and you could do some maintenance on the charger if possible. And in truth, if you have a spare breaker like I've shown here, you could temp in a secondary charger, a rental charger or a temporary battery charger into that breaker there while you're working on the other system. It gives you some flexibility for maintenance. So that is an ideal single DC system. Now, here's some systems that are poor design. Now, obviously, I've worked in the field for 20 years, and I've seen about as many of the poor designs as you can imagine. And one of the most common things is when somebody connects the battery cables onto the output cables of the charger. Now, it's not easy to see on this drawing here, so it just so happens I have a picture. And this shows you here. So this is, let me just turn my pen into, so this is the positive bus bar here, and this is the negative bus bar here. Now, they've connected the load cable on the front lug and they've connected the battery cable on the back lug. And don't get me wrong, this will work absolutely perfectly. In normal operation, this will be fine. But if you have a failure in your charger or in your battery, you are going to have to take a load outage in most circumstances, because you're going to have to disconnect one of these cables. And that means you have to loosen that nut and pull those cables apart, and therefore you will lose the connection between the charger and the load circuits, or the charger and the battery. So it's not a good design. And another poor design is when they connect the output cables of the charger and the load cables onto the battery terminals. Once again, you can't see it very well with this single line diagram, but you can see here that there's a very large terminal plate here. You can see the battery is down here, and there are 3 spare holes on this. So a lot of people say, okay, well, why don't I attach my load cable here? You know, you can have your load cable coming in there and everything will be fine. But once again, if you have to replace this battery, then you are going to have to remove that terminal plate and replace it. And therefore, you're probably going to have to take a disconnect on your load circuits. So not a great design. And there's another example here on a smaller battery where a lot of people will put the cable on this side here. They will have their lug going on that side, and the bolt will go through there. And once again, the 2 cables are in parallel. It will work absolutely fine, but you cannot remove the battery for service without taking a load outage. So not a great design, and there's ways that you can get around it. Now, here's another great system. It's a dual charger system, but with only 1 battery. So all we've done is replicated this whole box at the top here, excuse my terrible drawing, and we've put another system in parallel at the bottom here, identical systems. And as you can see, we do have a separate disconnect for each of those chargers, and then we have a disconnect for the battery here. So in this circumstance, let's say that rectifier number 1 or charger number 1 fails. What we can do is we can open this disconnect here, we can open the MCC disconnect, and therefore we know we are safe to work on rectifier 1 and do maintenance or even replace it if we absolutely have to. So it gives us lots of flexibility. And while we're working on rectifier 1, we know we have rectifier 2 here working absolutely fine, charging the batteries and keeping the load circuits powered. So this is a very, very good design. And the only difference on this slide is that for some systems, specifically usually for DC lube oil pump systems, where it is absolutely critical that the DC lube oil pumps run when the turbine needs to cool down, and we need to keep lube oil going to the bearings. So in those systems, they won't have a disconnect and they won't have an overcurrent device, because they want to make sure that the battery feeds the DC lube oil pumps at all times when the power is lost. So in some highly critical systems, you may see that the battery is just connected directly onto the DC bus without a disconnect. Let me just take a drink. But you can see on this drawing here, this is the Gold Star Award, because they have connected 2 chargers in parallel, going through individual disconnects here to the DC panel, but they've also connected 2 batteries with their own disconnects here. Okay, this means that if battery number 2 fails, you can open this disconnect here, remove the battery and replace it, and you still have battery backup from battery 1, and you still have 2 chargers feeding the load. So absolutely fantastic way. Obviously it's a bit more expensive, but this is by far the best design of system for your DC critical loads. And I hope you can see why that is from this drawing. Very flexible. You can open this breaker here, open this breaker here, and remove the whole charger. You still have this charger here and the two batteries here. So lots of backup, even if one complete system fails. Very robust way to protect your DC critical loads. So what we're going to discuss now is the power flow. How does the power flow through a DC system? And once again, there's a lot of confusion as to why we have chargers or rectifiers connected to batteries. A lot of people think that their design is to supply power to the critical loads. And in truth, in 99% of cases, the only reason we have a rectifier or charger here, the only reason is to keep this battery charged. So when we do have a power failure, then the battery is fit for service and will supply the load circuits. It's only there to keep the batteries charged. Okay. So the normal power flow, if you follow the green arrow, is your 480 will go into the rectifier. That gets converted into DC. The DC goes to the DC panel. And the only reason that the charger feeds the load circuits, and this is for, let's say, for example, for a 60 cell system, our voltage here is going to be 135 volts. Now, the open the open string voltage of a battery for 60 cells is going to be around about 128 volts DC. So you can see that 135 volts is more positive than 128 volts. So that's why the charger feeds the load circuits. It's just through design and the requirements of charging lead acid batteries. Okay. And then obviously we have a small amount of trickle charge current going to the battery to maintain their charge. Okay. Sounds like they're having fun next door. So if we have a power failure in our MCC, so 480 volts is lost, then what happens is the battery starts feeding the load circuits without any interruption whatsoever. And there's no switching involved. There's no transferring. It's just like you pulling the AC cable out of your laptop. You know, your laptop just carries on going regardless. It doesn't switch off and then switch back on again. The DC loads will not see any interruption in the power to them whatsoever. But do be careful, because there is DC from the battery. If this disconnect is closed, you will still have backfeed from your DC panel back into your charger. So please be aware of that. If you have a power outage and you're going to go in and check your rectifier, there's still a backfeed there. Okay. Oh, and I just wanted to say, I didn't say this at the start and I should have mentioned it. If you do have any questions, please type them into the chat bar. I tend to try and leave questions until all the way at the end of the presentation. That way it doesn't interrupt what I'm doing, and it lets us have a really good Q&A session at the end. But if something pops into your head while I'm doing something, type it into the chat bar and I will go over that at the end of the presentation. Okay? And that was just a good excuse for me to take another drink. Now, if the power comes back on again, so 480 is now available, once again, no switching is involved. The rectifier charger will come back on again immediately. And what it will do is it will start feeding the load circuits, because remember, it's got a higher voltage of 135 volts. And it will supply full recharge current back into the battery. So if it's designed correctly, then the battery will be fully recharged and it will have the ability to supply power to your load circuits as well. So the power flow for a parallel system is, as you can see here, the green arrows, both charges are in parallel. So they will go onto the DC bus at this point here, and they will feed the load circuits, and they will also keep the batteries trickle charged. And this brings up one of the most contentious points of paralleling DC systems is, should they load share? Now, I might go into this later on in the presentation. It's been a while since I did this one, but I'll go over this subject right now. In my opinion, now remember, it's only my opinion, there is absolutely no need, reason whatsoever for DC systems for two chargers in parallel to share the load. Absolutely none whatsoever. Okay, let me explain this. Let's say you set this charger at 135 volts and you set this charger at 135 volts. Let's say this cable is 10 meters. I'm European, sorry. And this cable is 20 meters. Okay, this cable here is going to have more of a cable drop. Okay, so that is going to affect the voltage. So really at the DC panel, you might see that this one here is going to have 134 volts and this one here is going to have 135 volts. And therefore, this one here is going to supply more of the load because it has a higher voltage. The charger with the highest voltage will supply the majority of the load. And that's not a bad thing. Okay, that's just the design of the system. But what's critically important, and people forget this, remember, the reason you have a charger connected to your system is to keep the batteries charged. And the battery needs to be charged at a specific voltage. So let's say this is 135 volts. Okay, we want the other battery to be charged at 135 volts. But once again, we have to measure this at the positive and the negative of the battery itself, and cable drops and everything will come back into the situation. So there could be a possibility for us to keep both batteries at 135 volts, but because of cable drops, maybe this one here needs to be 136 volts, and this one here needs to be 135 to maintain this 135 volts at the battery. Okay? And therefore, this charger here is going to supply more current to the load circuits because it has the higher voltage. And what people don't understand is, you know, you're probably, if you're like me, all shouting at the screen, oh, but you can buy load sharing. You can buy chargers that electronically share the load together. Yes, absolutely, you can. But what that does is it changes the voltage on the output terminals of the charger to make sure that the chargers share the load. So let's say all we care about is that this charger here has 10 amps and this charger here has 10 amps. The only control we have over that current is the voltage out of the charger. So we would have to increase one charger to make sure it supplies 10 amps while the other charger is doing 10 amps. And if we adjust one, that means we are going to change the terminal voltage of the battery. So I know that's a very long-winded conversation about load sharing. I personally don't think that it is necessary. You are messing about with the end terminal voltage at the batteries, which is not what you want to do. And people forget that. And you will, in most cases, either overcharge one of the batteries or undercharge one of the batteries, unless you size the cables absolutely perfect and the temperature in the battery room at both batteries is identical. There are so many parameters that affect load sharing. And in my opinion, just buy two chargers, put them in parallel, set them at the exact 135 volts at that battery, 135 volts at that battery, and then make sure that those battery terminal voltages stay correct. If A has all the load and B has no load, doesn't matter, in my opinion. If you want to test it, just switch one of them off, then the other one will take the load, or even easier, if you're scared about switching one of them off, press the equalize button on the one that has no load. And then that charger will then take all the current and you will see that it is working. Because that's usually what people want to see, is that both chargers are working. So I hope that explains load sharing and my opinions on it. And remember, they're just my opinions. So if you lose the AC input to one of the parallel chargers, what's going to happen is charger 1 will just carry on going regardless, supplying all the current to the DC panel, and it will keep both batteries charged. But do remember that there is a back feed to the other charger if you need to go in and find out what's wrong with the system. Okay? Hopefully that makes sense. Now, if we lose both MCCs, then what's going to happen is both batteries are going to take over and supply the load circuits. Okay? And once again, you're still going to have this back feedback of the chargers. But both batteries will be sized in order for them to supply the load circuits with the correct current for the amount of time that's necessary. Somebody's just said that the audio keeps dropping off. Is anybody else having issues with their audio? I do apologize if that's the case. This is usually a very stable platform. I'll just give 15, 20 seconds to see if anybody else sees that. Sorry, anybody else says that the audio. No, nobody else is having any issues. Okay, if you are having issues with the audio, just press the reconnect button at the top, and maybe that's going to help your connection. Thanks, everybody, for letting me know, because there's nothing worse than me talking to myself. My wife tells me that all the time. Okay, and let me just check here. Somebody did type in a question. Is it better that the batteries to be one string or two? It's always better if you have two strings of batteries, because that allows you to do maintenance on one string or replace one string, and the disconnects give you the ability to do that once the system is in the plant and up and running. This is all about maintenance once the system is installed, and it's always better to have two separate parallel strings. So thanks for that question. Okay. And then if we have a problem with Rectify 2 and we can't fix it, can't get parts, there's some issue and you have to replace this charger, then all you have to do, remember this cable here was connected here, is open that disconnect, put a lockout tag out on there, open this MCC, circuit breaker there, and put a lockout tag out there. And then remove the cables here, remove the cables here, and that allows you to take this whole charger out and replace it with a new charger. And you still continue to supply the load circuits and keep the batteries charged, and your loads will see no interruption whatsoever. They're all happy. Okay? So that's a very, very good reason to have parallel systems. Marcos is asking how to avoid that one battery feeds back to the other battery. In truth, it's not an issue unless there is a fault, and then you can put fuses that could clear a fault in one battery that would allow the other battery to feed into it. In truth, you could also have some kind of diode arrangement if you wanted to, but I don't think there is a need for that. I just think you should connect two batteries in parallel through their own disconnects, and you will be fine. Once again, that's my opinion. It just simplifies things. Having diodes in there, that means there's a diode drop across the diode. So if you set the voltage at the charger, there's going to be about a 0.6 difference between the charger and the battery. And sometimes people forget about that, and the batteries end up being undercharged. So just put them in parallel as far as I'm concerned. Okay. And when the power, if you want to replace a battery, my apologies, you can do exactly the same. All you need to do is open this disconnect, and you can do a capacity test on this battery, or you can replace it completely. And both chargers will supply power to the loads and keep the other battery charged. Easy as can be. Really, really great for maintenance. You don't have to take an outage on your load circuits to do work on this system. Okay, so hopefully that gives you a good overview of the best design of DC systems. Now, what are DC systems typically used for? Most common one is switchgear tripping and closing. Near enough all MCCs in petrochemical industry and at substations have switchgear tripping and closing. We need to be able to trip breakers in an overcurrent situation, even when there is no AC power to supply the tripping and closing mechanisms. Okay. The other one is DC Lube pumps and on turbines, which I mentioned earlier. Most turbines will have an AC Lube pump. So if for some reason the turbine goes offline and starts to slow down, you have to keep the bearings in that turbine lubricated to make sure that they do not overheat and eventually fail and cause the whole turbine shaft to bend, warp, and it can cause millions of dollars worth of damage to a turbine. So you have to have some system there that if the AC fails, that there is a pump that will pump the oil through the turbines even when you lose AC power. And that's what a DC Lube pump is. And they are extremely critical to protect turbines from basically blowing themselves to pieces when they are going through their cool down cycle. DC powered DCS systems, very common offshore, where instead of using 120 volts AC to their DCS, their distributed control systems, they take 24 volts directly from a DC distributed system into their DCS. Telecommunication systems, they use positive and negative 48 volts DC, and some instrumentation can require DC power. So in all of these circumstances here, they're all things that you need to work when you lose AC power. When grid power goes away, you need the loads to carry on working. Okay. I see some more questions coming in there. I'll try and answer them when I get to the end. So common misconceptions. And the first one is, for a 60 cell system, my battery voltage is 135 volts. Therefore, the battery must be good. Okay, we'll go into that in a minute. The second one is, I can disconnect my battery from the charger and the charger will feed the load circuits without any issues. Then we have the ground faults on chargers, very common misconception there. Oh, parallel, I knew I went into this later. Parallel chargers are not sharing, what's wrong? And then my switchgear charger has no low current. So we'll go over each of these individually. So the first one is, I have 135 volts on my battery. It must be a good battery. Incorrect. Very common misconception. So here's a typical lighting diagram for your house. Okay, you have 120 volts being fed to your house from the transformer outside. Okay, and then all of your light fittings are here. These are lamps. Okay, and if you measure across the two terminals on any of the lamps, you will measure 120 volts AC. That's on this lamp, or on this lamp, or on this lamp. You get 120 volts. And all lamps are lit, so everything's good. So follow me on this and see if you can see what's going to happen. Now, somebody has removed this third lamp. It's not there anymore. But guess what? If you get your multimeter and you go on the terminals to that lamp, even though it's not there, you're still going to measure 120 volts. Okay? The voltage is still there, but the lamp isn't. The lamp's not even there, so it can't be lit. So hopefully you can see where I'm going with this. So the same can be said for a battery. All I've done here is, instead of 120 volts, I've now got 135 volts DC. And now I've got 3 batteries here instead of 3 lamps. And if you measure the terminals on any of these batteries, the most positive and the most negative, you will get 135 volts DC. Okay? But if you remove one battery, you still have a cable that was supposed to go to the positive and negative terminals. And if you put a multimeter on the positive and negative terminals going to that battery, you will measure 135 volts DC. They're in parallel. Okay? So you will have voltage available. So if you have one battery at the most positive terminal and the most negative terminal, because you've got this charger here, you are going to measure 135 volts DC. Okay. But guess what? You remove that battery, you're still going to have 135 volts DC because of the charger. And this is where most people fall down. It's because one of the most common failures in a battery is an open circuit cell. Okay, one of the cells goes open circuits. That means current can't flow through the battery anymore. So the battery is useless, absolutely useless. But guess what? If you measured across the main positive and the main negative for that battery, even with an open circuit cell, you're going to measure 135 volts DC. So measuring the voltage at the battery terminals when the charger is connected gives you no indication of the state of health of that battery whatsoever. None. Absolutely zero. So that is the first misconception. And let me go to here. So this next one is, I can disconnect my battery while the charger is online. Oh, we hear this all the time. In theory, yes, you could, but it depends. Okay, because remember, the charger is supplying DC to the load circuits and the battery is being trickle charged. So if you remove the battery, what you can find, especially in older chargers, very old chargers that don't have any filtering circuits on them. They're quite common. They're still out there. I saw them all the time when I was in the field. When you have no filter inside of a battery charger, what tends to happen is the design was that the battery itself, because it has inherent capacitance, because it has plates right next to each other, it has capacitance, it acts as a filter. Okay. So while you have the battery connected, you have pretty good smooth DC coming out. But when you remove the battery, there is no capacitance anymore. So you're getting pure DC voltage, but it's pulsating DC going out to your circuits. And remember, the peaks of these DC are obviously dependent on how the SCRs are phased, but they're going to be quite high. And your load circuits don't like that. And especially for switchgear and tripping and closing systems, some of the relays will actually drop out with this form of pulsating DC going to the load circuits, and you will cause your MCC to trip. Okay, so to say that you can remove the battery out of service while you have a charger connected, in truth, you should really never do that. And here's another reason. A charger is usually sized for recharge time only. So let's say this battery here is a 100 ampere hour battery, okay? And the data sheet says that it needs 30 amps to charge that battery to get it back to 80% charge within 8 hours. That's the industry standard, okay? So therefore, most design engineers will turn around and say, okay, I'm going to make this charger, let's just say for ease, let's make it exactly 30 amps, okay? That's absolutely fine, because when the battery is called into action, once the power comes back on again, the charger will supply 30 amps to the battery and recharge it, okay? But that doesn't mean that your load circuits are only going to ask for 30 amps, okay? And I'll explain that on the next slide. Because remember, that's all now. The charger can only supply 30 amps. So if you had this battery locked out, the charger could overload if called upon which could cause a significant dip in the output voltage, because what a charger does to protect itself, if it went above 30 amps, the only control we have is to reduce the voltage out of the charger to maintain this 30 amps. And for switchgear systems, the common charge motor inrush current is somewhere between 20 and 30 amps. So let's say two motors for your tripping and closing supplies came on at the same time. That means you're going to see 40 to 60 amps. Okay, it's just going to be for a short period of time, but when you do that, the output voltage of the charger could go down to maybe 100 volts. And that could affect all the other loads that are connected to this DC panel and could cause them to drop out. So that is not a good situation. John's asking a good question. I thought the point of using this configuration was so you could remove the battery for maintenance. That's on a dual parallel system. For this system here, to answer your question, what you would need to do is, if you were going to take this battery out of service, you could either tie in a temporary battery into this point here, or because you have a free disconnect switch here, you could tie in a temporary battery into there, close this disconnect, and then open that disconnect, and then the temporary battery would give you backup while you do work on that battery. It was the dual parallel system that allowed you to take one system offline, not a single system. Okay, I hope that explained that. So the ground fault is on my battery charger. I've got something wrong with me, because I don't know why, but I love ground faults. It's a strange thing to admit, but I do. When I was offshore, we used to have a tool that searched for ground faults, and it was like a Sherlock Holmes thing. I really enjoyed looking for DC ground faults. So this is a subject that actually I'm really interested in. But most people think that because the alarm is on the charger, you usually have an alarm signal on your charger that says DC ground fault. They think because they see that on the charger, then the ground fault is within the charger itself. And that usually is not the case, okay? Because we have a isolation transformer in all of our industrial UPSs, okay? And in most circumstances, in fact, it's usually down to electrical code, the neutral of the input to the system will be connected to ground. Okay. Now, we don't even run the neutral to our chargers. We don't need a neutral for our system. So we don't even look at the ground connection here. But the important thing is there is isolation between the primary and the secondary of the transformer. Okay. So therefore, we're creating a separately derived source. And if we do not connect it to ground at this point here, then it has no reference to ground. Okay? So if you got a multimeter, let's say this is a 120 volt secondary, and you went on this terminal here to ground, what would you measure? And the answer is, who knows? Because there's no reference. So there should be, in theory, no voltage. There can be stray capacitance and other things given a ghost potential, and your meter will add some impedance to that as well. So you might see it start at 0 and then it start going up or something like that. But in truth, that's due to external references. There is no potential between this point and ground. And obviously that's exactly the same for the neutral to ground. There's just no reference. Okay. So as you can see here, I've now drawn the transformer and we have no connection to ground here. Okay. And I've put in a charger. Okay. And then the charger has its positive terminal and its negative terminal. And if we took a multimeter and we went between positive and ground, guess what? You shouldn't measure any voltage. But once again, there are things that could make you measure a voltage, and I'll go into those in just a moment. But it can be stray capacitance, other parts of the circuit. I'll explain in a moment. But in theory, If you go from positive to ground and negative to ground, you should measure 0 because there is no potential, because there is no reference. Okay. So everybody's shouting at me. Okay, so why, when I measure positive to ground and negative to ground, do I get 67.5 volts? Wow. That's because the charger manufacturer adds a circuit to detect ground faults, because we want to detect if there is a ground fault. And also remember this point. Having positive connect to ground doesn't give you an issue. Okay, you want to know that it's happened so you can clear the fault. It's only when the negative then connects to ground and has a separate fault that then you would dare have a problem. Okay. So in this circuit here, what the charger manufacturer did was he put two 5-watt lamps in series and connected ground to the midpoint here. Okay. Now, to get 5 watts, basically it's a 3 kilo ohm resistance. The lamp would have a 3 kilo ohm resistance. Hopefully you can follow me with this. So the charger manufacturer has now created a reference to ground. Okay. We've done that on purpose, so you know that there is going to be a ground. Now, in normal circumstances, both lamps are going to be half lit, because two resistors in series for the same value creates a potential divider circuit that has a ratio, not a ration, sorry, I need to fix that, a ratio of 50-50. So that means you're going to get 67 for a 135 volt DC system. You're going to get it 67.5 volts across that lamp and 67.5 volts across that lamp. Okay? So they're going to be half lit. I wouldn't say dimly lit, so they're going to be half lit. Okay. And then if we do have a ground fault, so the positive here has faulted to ground externally somewhere, then the potential across this lamp now, because we have taken a direct short across that lamp, is now 0. And now all the potential is across this bottom lamp. So that bottom lamp shines really, really bright. And that would indicate that you have a positive ground fault. Okay, positive has shorted to ground. Okay, so that makes this point here 135 volts, and this point here is 0. So the full potential is across that lamp there, and the lamp will light bright and tell you that you have a ground fault. Now, the easiest way to find a ground fault, now I understand in most circumstances this is very difficult to do because the plant won't allow you to switch off your load circuits. But the first thing that you need to do is open up the output breaker on the charger. Because remember, the LED and the alarm circuit for the ground fault is within the charger itself. So if the ground fault is on this load circuit here, if you disconnect the charger and the lamp goes off and it goes back to normal, you have now said, okay, the ground fault is not in the charger. It has to be somewhere upstream of this breaker here. Hopefully that makes sense. So that way you've ruled out that it's not in the charger. And then, unfortunately, what you need to do is you need to go out to each individual load circuit and open each one until the LED or lamp on the charger goes off. There is another way. You can use a ground fault detector. And basically what that does is you connect a signal generator to the pole that has the fault. So let's say on this one, it's a positive. So you connect one lead to the positive and then one lead to ground. It sends a signal only through the positive ground circuit. And then you get sensors, basically transducers that you can put around each cable. So you could put it around this cable. And if it says that there's a ground fault, then you move to each individual circuit. and then it will show you which of these circuits specifically has a ground fault on it. It's a very good piece of equipment to find ground faults. Okay. My parallel charger is not sharing the load. What's wrong? I'm going to skip this because we went over this in detail earlier on. Nothing, probably. And it goes on to say that the most important thing is to keep the battery charged at the correct voltage for the battery. So I'm going to skip all of this. It is a myth that chargers need to share the load. I'm just going to say that. Once again, my professional opinion. What's this one here? My switchgear charger has no low current. Oh, a very popular misconception. A lot of charger manufacturers, and I think we have the option as well, is you can get an alarm that will alarm on your charger for low current situations. Because most people say, okay, if I have no current on my charger, then there's something wrong with it. And that's not necessarily the case. Let's say that this is set at 0.5 amps. And remember, well, not remember, but know that measuring very small amounts of current is very, very difficult because we're talking about millivolt sources that convert the amps into millivolts, and we have to compare that against a reference signal. It's very, very difficult. Okay, so really anywhere below 5 amps, it's very difficult to measure it accurately. But, for example, on switchgear systems, the only load that you have is the auxiliary circuits, so lamps and maybe some relays, very, very low current. So you could, in theory, only have 0.3 amps, because if the battery is fully charged, you could have a very small amount of current to trickle charge the batteries, milliamps, and then your load circuits could be low. So in truth, in normal operation, the output of your charger is okay if it's 0.3 amps, if that's what the load circuits are asking for. So you are going to alarm because the low current threshold is 0.5 amps. And that gives lots of false alarms on systems. And believe me, I've been called out to so many systems. Oh, we've got an alarm on our charger. And I go out there and I realize that it's the low current alarm, and there's nothing wrong with the system whatsoever. And I just have to tweak the setting for the low current or disable it, because I'll have a conversation with the plant and say, look, you really don't need that low current alarm. Okay. And that's the last one. So any questions? I hope that was informative. Let me go through the questions, the chat bar. And while I'm going through that, if you have any other questions, just let me know. Thoughts on adding protection, e.g. fuse disconnects between batteries and the DC panel for arc flash mitigation? Ooh, very, very good question, Joshua. And that is something that a design engineer would have to look at very, very carefully, because you would have to rate the fuse in such a way that it wouldn't blow if you had a fault on one of the DC circuits that you wanted to clear with the battery, but you wanted to keep all the other circuits powered. So it's difficult, but if you're going to put anything, it should be a fuse disconnect rather than a breaker, in my opinion. But the fault analysis would have to be done, and you would need to stagger the current correctly to make sure that that main DC fuse does not go before any of the other smaller protection goes. I hope that answered your question. If it didn't, let me know, and I could get one of our other design engineers to get in touch with you. How do you size rectifier output? Is it based on 100% of loading? Yes. Whenever you buy a UPS and a battery system together, the battery is always sized at the full load current of the UPS or the system that it's connected to. So when you have two parallel batteries, another misconception is that you could put a 50% battery and a 50% battery in parallel, and therefore when they're connected together, you do get 100%. But the obvious downfall of that is if one of those batteries fail or you have to replace one of the batteries, then you are at a 50% less capacity during the time. And remember, most batteries, I was actually in a meeting with Enesys yesterday, and they're saying that the lead times on batteries just now are ridiculous. There's some quoting 20-week lead time. So, you know, you could be running at 50% capacity for 20 weeks waiting on a new battery to come to replace your battery. So if you are going to have a parallel system, you should always have 100% batteries connected in parallel. Yes, it's more expensive, and yes, you have 200% capacity in normal operation, but it prevents any issues after the installation of the system and it's in operation. Okay, somebody's asking that I show the common misconception screen once again, so let me go back to it. The only thing about this webinar jam is it's not a real PowerPoint presentation, so I can't choose which page. I've only got a previous and next button, so I have to go back, and it's not very fast. I'll get there though. While I'm getting there, we have another question. If you have the battery disconnected on a switchgear and you have a fault causing the breaker to trip, can the charger respond quickly enough? No, absolutely no, it can't. And that's one of the reasons why you should never have a battery disconnected from your switchgear system. You should always put a temporary battery in place before you remove the other battery, because any fault or transient load on that system will inevitably pull down the voltage of the charger. In truth, it may still clear the fault depending on how high the fault is, but in doing that, it's going to reduce the output voltage, because remember, the only way that you can limit the current on a charger is by lowering the voltage, because it's proportional, inversely proportional. So to reduce the current, you have to reduce, it's not inversely proportional, what am I talking about? To reduce the current, you have to reduce the voltage. And when you reduce the voltage, you can affect everything else that's connected to the system. So that is why you should not disconnect a battery from a DC system. People will sell you a battery eliminator. To me, it's the most ridiculous thing I've ever heard of in my life. Sorry for any companies that sell battery eliminators. There's no such thing as a battery eliminator. All they do is put some additional capacitors inside that charger. So if you remember my slide, if you go back, they put additional capacitors in there. So let me get to the slide that mentions that. Come on, I hate this. There we are. Okay. What they do, the charger, for a filtered charger, they will have a bank of capacitors connected here. And for a battery eliminator, all they do is put a whole load more capacitors in there. So when you remove the battery, it does keep the voltage going out at 135 volts DC. But going back to Bill's question, if you have a fault out here and you need to clear it, the exact same thing is going to happen. The output voltage of this charger is going to drop down without a battery. So if somebody tries to sell you a battery eliminator, get them to explain how it eliminates the battery. Does it have any capacity or backup time to replace a battery? The answer is no, absolutely not. The capacitors will only work for less than a second, pretty much, depending on the load circuits. Capacitors do not replace a battery. Do not be fooled. Okay? Do you think I have an opinion on that? Sorry, but it does. It drives me insane. And it's what marketing and sales teams do. Sorry, marketing department. I love you, but I'm a technical guy. I believe the answer to the question is to include a blocking diode in the system. Yes. And let me see. Let me bring a whiteboard up. Let me do this. Let's make the whiteboard completely. Let's do this. So if you have two chargers going in here, okay, and you have a battery here and a battery here. What some people say is, and it depends on the design engineer, you could put a blocking diode there and a blocking diode there and connect the systems in parallel out that way there. And that way, this battery here can supply power out to the load circuits. But if there was a failure in this battery here and it had a short circuit or something in there, then this battery would not be affected because this blocking diode here, this cathode here, would not allow it to feed back into that battery. So you can use blocking diodes, and many people do. I'm just not a fan of them because it's an additional point of failure, in my opinion. But I'm not as passionate about that as many other things. Okay, so the rectifier should be loads and battery. Well, John, once again, if you go back to the start of my presentation, rectifier and battery charger are two interchangeable terms because they do exactly the same thing. The term rectification means changing AC into DC, and a battery charger changes AC into DC. So the differential is, for a rectifier, in truth, it wouldn't have a battery connected to it, but that's not the case because many rectifiers do have batteries connected to it, and people will just call it a battery charger. Am I rambling, or does that make sense? But you should always have this battery connected. Because like I said, the most common thing is everybody's got to conform to IEEE standards for their battery capacity tests. And if you're a NERC related plant, you have to do your battery capacity tests at a 3 to 5 year period. So somebody has to come in and disconnect the battery and do the test. And a lot of people will say, well, just for ease, we'll just open the battery, disconnect, and leave the charger supplying the loads. Don't do that. Get the battery company to temp in a battery for you and make sure that battery is sized correctly to match the battery that they're testing. Okay, is floating voltage of battery less than output voltage of charger? Norik, very good question. And it goes back to the misconceptions as well. Because they are in parallel, they're going to seem to be exactly the same voltage, because they're in parallel. If you have any two, let me see if I can do this. Go back to my whiteboard again. If you had this charger and this charger, okay, I'm going to probably draw it wrong. And let's say we connected these two charges in parallel. So this is positive and it goes up to the positive on there. And then this is the negative and that goes down to the negative here. If this charger here, if its output was 50 volts and this charger here was 130 volts, if you look, they are now connected in parallel. So if you put your multimeter on this terminal here and this terminal here, which in truth is a parallel point between the two chargers, you're going to measure 130 volts. So would you say that the charging voltage of this system for both chargers is 130 volts? The answer is no. This charge voltage is doing nothing. It's at 50 volts. Okay. This one here is 130 volts. It is doing all the work, but all you will notice with a multimeter is that it's 130 volts on the output. So I suppose what I'm trying to say here is if we remove, that's not great. Let me make it bigger. If we remove this charger here, and we make that a battery, and we make this a battery, okay, and let's make that 135 volts because that's what it should be for a 60-cell lead acid battery. In truth, if you disconnected, let's put a disconnect in there. If you disconnected this battery relatively quickly, that battery will go down to around about 127 volts. That is what's called the open cell voltage of the battery. And it will sit there for a very long period of time. And then as soon as you close that disconnect, it will go straight back up to 135 volts because it's in parallel with this charger here. Okay. So in truth, when you say is the floating voltage of the battery less than the output voltage of the charger, they're both the same. They are 135 volts. But all we're doing, what I'm trying to say is, as soon as, I'm trying to think of a way to explain it. As soon as you lose power to this charger here, and that 135 disappears, and you had a multimeter connected across here, you will see it go from 135 volts way down to 127 almost immediately, because that is the open circuit voltage of this battery. The additional 8 volts is what's needed to trickle charge the battery to overcome the chemical losses inside the battery cell. Hopefully I have explained things and not confused things even more. That's not my goal. So John says, but it needs to be able to recharge the battery from full current and still feed the panel loads. So yes, so yes, you are correct. So let's say, going back to John's question about how should you rate the charger. Okay, let's say the design engineer has come up and said, okay, every load that we're ever going to have is 100 amps on this panel here. Okay, that means they size the battery. Let's say we want 3-hour runtime. We want to size a battery that's going to give us 100 amps for 3 hours. So you choose whatever battery will give you that. Now for the charger, we're saying that a 30 amp charger is going to be fine to recharge that battery. But as John says, yes, you have to factor in if the panel was pulling 100 amps, that you've got to factor in that the charger can't supply all of that current on recharge. But what you've got to understand is that when you put the battery back on charge, this will go back, the battery will go back to doing 70 amps in the battery. I see what you're saying. We'll do 30 amps. So a good design engineer, you are correct, should rate this at 130 amps. But the issue that we always have is that the DC panel is never ever going to have 100% load on it. That's just for design specs. But I do see your point, John, and my apologies if I misled you earlier. A good design engineer will factor that in into the system to allow the DC panel to accept 100 amps and have the 30 amps spare to charge the batteries. That's a good design engineer. Unfortunately, 20 years in the business has shown that that has not been the case. So good spotting, John. I like to be kept on my toes. Okay, so that's 8 minutes overrun. That's not bad for me, actually. I usually yatter on for ages after the 1 hour period. So 8 hours isn't too bad. So any more questions before I go? While I'm waiting for any more questions, I'd like to thank you for your time. Really, really appreciate you taking time out of your day to listen to me rambling on about DC systems. I hope there was some interesting... Oh, Bill saying, what about my question on bus voltage? Let's go down, Bill. I'm glad you're paying attention. If you have a loss of power and the battery discharges into the load down to 105 volts DC, then the power is restored and the battery charger outputs at 135 volts. What's the voltage on the bus? Very, very good question, and I'm glad you pointed that I didn't answer that. And the answer is it depends. It depends if the charger is rated for the full load current, just like we discussed with John's question. If in most cases, the charger will go into current limit of some form. And remember what I said, to The only way we can limit the current is by reducing the voltage. So in most cases, the charger is going to, when you put a fully discharged battery back online, it will go into current limit. And therefore, I can't tell you, Bill, what the voltage is going to be, but it's going to be above 105, obviously. But if the charger has been fully sized, then it could, in theory, go straight to 135 volts DC. And in systems like that, you will hear the charger going, really supplying a lot of power back into the load circuits and the battery itself. And I've seen many, many systems like that. So the question is not as easy to answer as you would think. But if the charger is capable of supplying all the recharge current to the battery and the load circuits without going into current limit, yes, it will go straight back up to 135 volts DC. Did that answer your question, Bill? Please let me know. But like I was saying, I really appreciate everybody taking time out of your day. I do realize you're all very, very busy people. And it really makes me feel good when you spend your Wednesday afternoon with me. As Taylor has mentioned in the chat bar, if you need additional assistance, you can go to our website and the link is there. And Taylor, can you put the link to the YouTube site in there as well, so the guys can check out where the YouTube site is? There we go. It's as if you had it ready and waiting. So also, as part of the communications, you will receive a survey after this presentation. Please take the time to fill it out. I read every single one of them, and I want to know what you want me to discuss going forward. Today, I had to go over something that we had done previously because I didn't receive any good topics from the last surveys. So please, if there's anything at all to do with batteries, DC systems, UPSs, inverters, anything at all to do with backup power supplies, please let me know what that is, and I will try and create a presentation around that subject and answer questions for you. So thanks for the nice comments, everyone. Hope you enjoyed it. We will be doing another one next month. Usually it's on a Wednesday in the middle of the month. Look for your emails. It will tell you when it is, a week before we plan it. And take care. Enjoy the rest of your Wednesday. And thank you for spending the time with me today. It was a pleasure. Thanks again. Goodbye.